I'm Dylan. I'm a PhD student at King's College London in the Safe and Trusted AI CDT. And I'm going to be presenting some work on, mimicry and the emergence of cooperative communication. So without any further ado, I'm just going to jump into a little bit of background, if I can press the buttons. Okay. So I'm going to start out with the framework of multi-agent reinforcement learning, because that's kind of where a lot of this work is kind of situated. So here we have some set of agents. They may be homogeneous or heterogeneous, and they're each observing some environment that they share. So this is kind of a shared embodied space, and they're each receiving some kind of reward, some observations, and taking some actions in that environment over a sequence. And the general formulation of this is what we might call partially observable stochastic games. But what I'm interested in this case is the cooperative setting, which is a DEC-POM-DP, so that's just another bit of jargon for you. And here we're basically just constraining it such that all the rewards are the same for the agents over time. So they have a kind of assumption of cooperative behavior or cooperative incentives. So that's a little bit in contrast to some of the talks we've just seen, where cooperation isn't necessarily a given. And what we're going to be focusing on in this work is about communication and its ability to facilitate that cooperation that we need to happen. So one sort of area of research where people are interested in this is emergent communication. And this spans kind of evolutionary methods as well as reinforcement learning methods. But the general framework looks sort of like a bit of an extension of the pictures I've just showed you. What we're looking at here is this kind of expansion of the action space and the observation space of all the agents in the system. So you can kind of imagine any sort of network connecting these agents, but each agent now has some special communicative actions they can take. So they can send a message directly to another agent. And this can, there's many different ways to formulate this. It can incur a cost or not. It can be at the expense of taking other actions or not. So it's kind of quite a general framework. And we call it emergent communication because what like Theodore was talking about earlier, originally these signals have no particular meaning. They are just discrete, choices that the agents can make. And the meaning or the semantics of these messages gets assigned over time through the optimization process. So people are really interested in studying what kinds of communicative strategies or protocols kind of emerge from this. You can get kind of like proto-language-like structures. And in particular, people have been quite interested in this field for the last years or so, in kind of contrast to the language modeling style approach to the language. Language models obviously capture the kind of statistical relationships between tokens in a corpus, whereas what emergent communication tries to sort of talk about is the functional uses of communication. The communication is grounded in some sort of task. It refers to things in some kind of shared environment. So people quite like this emergent communication framework as a tool for exploring that. But before I talk too much, I don't want to give the impression that I'm talking about the evolution of language in this talk to anybody who's a member of the French Academy of Sciences in 1866. You sort of know that they famously sort of banned the discussion of the evolution of language. So, hold off on the gallows, please, on that. So the thing that I want to focus on in this talk, and the thing that sort of motivated this line of research, was this observation that learning to communicate or evolving communication is really hard. And I kind of point towards what I see as this sort of chicken and egg problem. And it sort of comes down to this. A signal is only useful, it will only be selected for or only be reinforced if it induces some useful behavior in the listener of that signal. That's kind of the framework that we're looking at. But on the flip side, signals that don't already carry useful information are not going to be useful to pay attention to. If you're a listener, why would you adjust your behavior to signals that don't carry any information? And I won't linger too much on the sort of formal arguments. The paper includes a lot of kind of theoretical discussion of this problem, but we can sort of briefly just look at a sketch of what this looks like. So imagine you're some listener And this is the beginning of a training run or beginning of evolution. And we're considering just a very simple situation. There's some hidden variables, and yeah, there's some hidden variables, and we're going to take some actions. We're going to receive some message from a speaker, and our utility is going to be given as a function of these things. So our expected utility, if we receive some kind of message, is just kind of looking over all the possible hidden variables, and we have this probability distribution of what is that hidden variable given a message. But if the message is conveying no information, well, then the probability distribution sort of collapses, and we're unable to get any information, unable to change our behavior. So we aren't incentivized to do this learning problem. Now, this is an idealization. In practice, small variations will be picked up on by evolution or reinforcement. In effect, the listener, the speaker might just happen to signal some useful information, and we can maybe learn from that. But it's going to be very slow, and it's going to be very hard. So the title of the talk introduced this, or sort of alluded to this idea of mimicry. So what did I mean when I was talking about mimicry, and why do I think this is an interesting sort of intersection of these problems? So mimicry is just like this really interesting sort of natural phenomenon. It's sort of first properly described by this biologist, Bates, and he kind of posed it as this idea of there's a mimic and there's a perceiver, and then there's some model which the mimic is trying to replicate. So you have all these kinds of things here where, the butterfly's wing looks like the eye, which is supposed to deter predators. And in particular, usually it's framed in this adversarial relationship, right? So you have aggressive mimicry, where a predator is trying to lure in some prey, or defensive mimicry, where the prey is trying to get the predator to sort of not come over to them. And that's kind of in contrast to what I've been talking about so far, right? I've been talking about the cooperative setting. So in order to sort of pull these things together in the way that I was thinking about it, what we have here is this idea that it's hard to evolve communication because you don't have any reason to change your responses to a signal. But if there was already a signal that carried some useful information, well, then you would obviously pick up on that if you were learning or evolving. So the hypothesis that we kind of explore in this paper is this idea that if the speaker has the capacity to mimic a signal that already generates some or carries some useful information, then that kind of may bootstrap or speed up the evolution of that communication. That's the kind of like hypothesis that we look at. There's, as I said, a bunch of analysis, sort of going back to that sort of brief formal argument to sort of explore that in the paper. But I think just looking at the empirical results is what I'm going to focus on now. So in order to test this, we sort of set up a pretty basic simulation. It's a sort of grid world. And the idea is that both of these agents, represented by these blue circles, they need to go to some goal location. And this goal location is the star. But the star occasionally emits a signal, but that signal is only heard if you're particularly close to it. The agents themselves can also emit signals, and those signals can be heard no matter where you are. What this may look like is, in order to make this actually possible to do mimicry, you have to not be able to tell the difference between a signal that's emitted by the goal and a signal that's emitted by another agent. So in order to do this, you kind of have this spatial sensor system where you have a series of sensors that kind of tell you where a signal is coming from relative to your location. And that can be used to distinguish between to guide you towards a particular location. So here we have the perspective of a single agent in the middle there, and there's a goal on the left that's emitting the signal A, and there's an agent on the right that's giving a B, and you have these sensors, and they kind of allow you to see, okay, there's probably something in the bottom left, and there's probably something to my right. I don't know what those things are. I don't have direct observations of those things. But that's the sort of way in which these agents perceive the world around them. And this is the sort of motivation for this is because you can't determine whether or not a signal is coming from one source or another. You can essentially learn a behavior in one situation that can be repurposed for another situation. I'll go into that in a little bit more detail. The experimental setup, we tested with reinforcement learning and with evolutionary algorithms. So we were looking at the multi-agent PPO algorithm and the simple genetic algorithm from this paper on multi-agent evolution with reinforcement learning. And we're using these libraries, so JAX, MAL, and EvoSax, and everything else is written in JAX. Makes it really nice, really fast. Yeah, you can run lots of seeds very quickly. And then we can adjust this, as I said, capacity to mimic a signal by basically changing the overlap between the resource signals and the agent signals. So if these are completely disjoint sets, well, then you always know that the signal is coming from one source or the other. If they're overlapping to some degree or completely overlapping, then you have this ambiguity. And that's kind of the question that we're looking at here. So when we run this experiment, what we see is that indeed the capacity to mimic does seem to allow the evolution of communication to happen faster. I suppose if you ran that for longer, it looks like eventually the ones without the capacity to mimic would catch up. But certainly it's a lot faster at the beginning. So this signal overlap question is, again, how we know whether or not the mimicry is available. And then some similar kind of results for multi-agent reinforcement learning, although there's a bit of difference here. In particular, multi-agent reinforcement learning just seems to be kind of a lot better at doing its job. So it was pretty good in almost every situation. One of the major things that did seem to be a factor was without the capacity to mimic, there was a lot more variance in the improvements in the agent's performance. And one final thing is just analyzing the mimicry itself, seeing when it's happening. And what we do here is we sort of realign each of the training runs so that we get them sort of starting at the same point. When you just sort of run it, sometimes it just happens to get lucky and it happens to start communicating earlier. So if you realign them, so they all start gaining reward at the same time, and then overlap that with the frequency in which mimicry is happening, we see this quite interesting spike where as the reward is increasing, it's going in tandem with this increase in mimicry. So it does seem to be the case that the mimicry is the thing driving the emergence of this communication in this setting. And there's some other interesting things. I think this environment has some interesting things that I didn't particularly explore. So you can see that the mimicry actually seems to decrease as a proportion over time. And I think that's to do with the idea that it sort of gets communication off the ground, but then it sort of moves away from that because it's actually a source of ambiguity. And you don't actually always want to be ambiguous about the messages. So that's a kind of pretty brief overview of the work that we did. I just want to finish on this kind of idea that the setting that we looked at is quite specific, but I think this is something that actually appears quite often in multi-agent systems, or what we maybe even think of as just single-agent systems, because you're sort of composed of a lot of cooperating parts in just many different situations. So in particular, I think it has this interesting relationship to this idea in evolutionary biology called revolutionary repurposing from this biologist Neil Shubin, who I think this book I really like. And the idea there is that evolution's often progressing by repurposing old structures. And in this case, we're sort of thinking about behaviors being repurposed. You know, you learn to respond to one signal, and then another agent says, oh, you've developed this really interesting behavior, this really useful behavior. I can take advantage of that. I can repurpose your abilities for our collective performance. So that's the kind of way in which I think this particular angle actually fits into a lot of other systems. So I think it's quite an interesting area. But yeah, with that, thank you for your attention. And if there's any questions, let me know.